Okay, so welcome to section 1.1 of Math 104. So this is functions and function notation, which I hope will be all review. So functions and function notation. Meaning basically f of x. Okay, so definition. First thing is a definition. So a relation, that's the first thing we'll define, is a relation. Let's call it capital R. Is going to be equal to the set of all x comma y such that the set of x's is the domain and the set of y's is the range. So they're ordered pairs, a set of ordered pairs. So let's note. So the input or the domain. So the input slash domain x is the independent variable. Independent variable. So x is the independent variable. The output or range. So the output slash range y is the dependent variable in that it depends on what value of x we plug in. So the dependent variable, Okay, let's do another definition. One we should know, so definition. And this is a function. So a function is a relation. So it's a set of ordered coordinates. So a function is a relation. But what type of a relation? There's something special about it. So such that for all values of x in the domain, this implies that there exists a unique y in the range such that f, how do I want to say this? I'll just leave it as that. There exists a unique y in the range. So that is i.e. it est, i.e. each input x, I'll write it this way, each input x from the range produces a unique output y. Okay, so notation. I used this symbol. There exists, and then I put an exclamation behind it. This is read aloud. There exists a unique. So with that exclamation point, there exists a unique. That's what it means. Okay, so for example, are the following relations, or how do I want to say this? Are the following relations functions? So are the following relations functions? Remember, relations are just set of orders, pairs. Are the following relations functions? question mark. So number 1. Let's say I've got the set of ordered coordinates. Let's say I have 3, 1. Remember, this is x, y. Then the next one is 2, -1. Then the next one is 5, 2. Then let's say 4, 1. So we have 4 coordinates here. So what I'm going to do is I'm going to look at x versus y. And actually, let me put this a little bit farther away. And I'll show you what I'm going to do here. Okay, so the first x I have is 3. And 3 maps to, what does it map to? Maps to 1. Okay. The next x I have is 2. And that 2 maps to -1. Agreed? Oops, that should have been a 1 there in purple. Let me write that in purple. The next x value I have is 5. And that is associated with the y value 2. And finally, the last x value I have is 4. And that gets sent to the y value of 1. Okay, so what does this mean? That means each x, so each value of x goes to, actually I should probably put goes to in pink, goes to a single value of y, right? A single value of y. So what this means is that it's a function. A function. So 3 goes to 1 and goes to 1 only. 2 goes to -1 and goes to -1 only. 5 goes to 2 and goes to 2 only. 4 goes to 1 and goes to 1 only. Now notice both 3 and 4 for values of x's map to 1, but that's okay. So now let's see what happens if I consider this next relation. So let's say I have 2 going to 4. Then let's say I have 2 going to 3. Then let's say I have 1 going to 3. Then let's have 5 going to 2. Okay, so once again, let's look at x and y. Okay, so for the first value of x, I have 2 mapping to the y value 4. But in the next case, I still have 2 mapping to a different value of y, namely 3. That's not unique anymore. 2 is no longer producing a unique value for y. Then my next value of x is 1, and that maps to the y value of 3. And finally, we have the x value of 5. Oops, let me put this here. 5, which maps to a y value of 2. Okay, so notice that for x equal to 2, this maps to both, y equals to 4 and y equals to 3. So that is, i.e., let me do this a bit darker purple, i.e. y is not unique. Well, since y is not unique, that means that this is not a function. So not a function, because the y value has to be unique. Okay, so let's note. So given a relation in x and y, so given a relation in x and y, so usually that is an equation. Remember, equation means there's an equal sign. Do I have enough room there? Kind of scrunch that. That is an equation. So if there exists a unique y, when isolated, then y is a function in x. Okay, so what do I mean by this? Let's see an example. So for example, so determine whether the following relations are functions in y. Are functions, in x. Are functions, period. So let me just write it that way. So determine whether the following relations are functions, period. So number one, let's say I have 2x minus 3y is equal to 6. So my goal is to solve for y. So let's say I have 2x minus 3 times y, I'll do y in purple, because that's a guy I want to isolate, is equal to 6. So my first step is to subtract 2x from both sides. So I get negative 3y is equal to negative 2x plus 6. And the final step is to divide everything by negative 3. So I get y is equal to 2 over 3x minus 2. So that's a single value for y. So that implies it is a function. There's only one value for y. So is a function. Okay, well, what would it mean to have two or more distinct values for y if there are no numbers involved? So let's see what I mean. Let's say I have x squared plus y squared is equal to 25, which is a circle of radius 5 centered at the origin, but we'll get to that later. So we have x squared plus y squared is equal to 25. So subtracting x squared, I get that y squared is equal to 25 minus x squared. Now, when I take the square root, do you agree that the square of negative 3 is the same as the square of positive 3? So whenever you take a square root, you have to tack on a plus or minus. So plus or minus the square root of 25 minus x squared. Oops, let me draw that a bit better. So what that means really is that y is equal to two things. So y is either equal to the positive square root of 25 minus x squared, or y is equal to the negative square root of 25 minus x squared. So there's two possibilities. And because there's two possibilities, this is not a function. So two possibilities. Or t's. So not a function. because it's not unique, not a function. Okay, let's do another one. Number 3. 1, 2, 3. So let's say we have that y cubed is equal to x squared. This is actually a good one. So we have y cubed is equal to x squared. Now, in order to solve for y, I would need to take the cubed root of both sides. But the cubed root cares about sign. So when I take the cubed root of x squared, there is no plus or minus. So it's unique. There's only one. Sign matters. There's no plus or minus for any odd indexed root, and we will get to that. So this is a function because there's only a single answer. Now, had I done it differently, had I said, okay, number 4, if we had done maybe y to the 4th, or no, y squared is equal to x cubed, that would be different, right? Because a square root, when you square something, if it's positive or negative, it'll become positive. So if I take the square root, I have to account for that. So y will be either plus or minus the square root, and this is purple now, the square root of x cubed. So that means that y has two values. It's either the positive square root of x cubed, or it's the negative square root of x cubed, which is two distinct answers, which means it's not unique. So two distinct answers implies not unique. Not unique. And if it's not a unique value for y, it's not a function. So not unique, hence not a function. Not a function. Okay. So let's recall. So when evaluating a function, we replace each instance of x with the point given. So when evaluating, and the word evaluate is what I'm focusing on here. So when evaluating a function at a given point, we replace each instance of x. We replace each instance of x with, how do you spell with? W-I-T-H, with that value. So this means evaluate essentially means given x, find y. Given x, find y. I don't know if I need that comma. So given x, find y. That's what evaluate means. You're given a value for x, you want to find the corresponding value for y. So for example, so let's let f of x be equal to x squared plus 1. So evaluate the following. So number 1, let's evaluate f of x plus h, which is kind of miserable. Actually, let me do that second. Let me make life easier first. Let's just do f of 3 first off. Okay, so I know that f of x is going to be x squared plus 1. So what that means then is that f of 3 what I'm going to do is I'm going to replace each instance of x with the value I'm plugging in, right? So this becomes 3 squared plus 1, which of course is just going to be 9 plus 1, which is 10. So this is f of 3. Let me copy and paste this a couple times. F of 3 is the value for y. F of 3 is 10, right? Okay, let's do another one. Let's do number 2. And hopefully this is all review. Remember, we've dealt with functions before. Now let's do the ugly f of x plus h. So once again, we know that f of any value x is that value of x squared plus 1. So what this means is that if I take and I plug in to the function the value x plus h, I have to look at x plus h as a singular entity. So it now becomes x plus h quantity squared plus 1. So that whole x plus h is the 3 that I had above. So simplifying, let me copy and paste this a couple times. I have that f of x plus h will be, I can expand the binomial here if I care to, first guy squared, x squared, plus twice the product of the first and the second, plus the second guy squared, plus 1. So there we are. That's f of x plus h. There's nothing more I can do. Nothing can be combined. So number 3. Let's kick this up a notch. Let's evaluate f of x plus h, which I've already done. But then let's subtract from that f of x, which is the original function, but divide it by h and simplify. Okay, so I want f of x plus h and I want to subtract from that f of x. And then I want to divide all of that by, actually, what color should I use? Let's use orange. No, orange is not going to look nice. Let's pink. Divide all of that by h. So what does that give us? So we have that f of x plus h was x squared plus 2xh plus h squared plus 1. So that's my first guy. That's my f of x plus h. And I'm going to subtract from that f of x. So what was f of x? It was x squared plus 1, right? So I'm going to subtract from that x squared plus 1, the original function, f of x. And then I'm going to divide all of this by h. Okay, so what I'm going to do now is distribute the negative inside here. And I notice what happens is that positive x squared and negative x squared will reduce. Positive 1 and negative 1 will reduce. So what I'm left with then in the numerator is 2xh. 2xh plus h squared, and in the denominator I'm left with h. But I noticed that each term in the numerator has a factor of h, so I'll factor one of those h's out. So now I have h times the quantity, 2x plus a single h. Remember, we just divide each term by what we're factoring out. And so now the h's reduce, h over h. And when all is said and done, this simplifies to 2x plus h. Okay, so there we are. Okay, let's do another example. So let's let, this is evaluating, right? Let's let f of x be the square root of x minus 5. So let's evaluate the following. So number 1, let's evaluate f at 36, say. So I know that f at x is going to be the square root of x, from which I'm subtracting 5. So what this means is that f of 36 means wherever I see an x in the original function, I'm now replacing it with 36. So the square root of 36 minus 5. Oops, so that's going to be 6 minus 5, which is 1. So f of 36, the value for y, when x is 36, is 1. Okay, so for the second guy, let's evaluate f at x plus h. Okay. Well, we know that f of, did I do that? Yeah. F of x is the square root of x minus 5. So this means that f of x plus h is simply the square root of x plus h, from which we're subtracting 5, and there's nothing more we can do. There's no more simplification. But let's evaluate f of x plus h, from which we're subtracting f of x, the original guy, and divide it all by h. And rationalize. Rationalize the numerator. So this is going back to algebra. Okay, so we want f of x plus h. Pardon me, oh my goodness. F of x plus h. And we're going to subtract from that f of x and divide that all by h. So what do we get? Well, what was f of x plus h? It was a square root of x plus h, from which we subtracted 5. We're going to subtract from that f of x, and f of x was just square root of x minus 5. Then we're going to divide all of that by h. So notice if I distribute the negative inside, I'll be able to reduce. I'll have negative 5 here, minus a negative 5 here, goes away. So what do we have? We have the square root of x plus h. And then minus the square root of x. And all of that is divided by h. So I'm asked to rationalize the numerator. So what that means is we multiply by the conjugate. Do I want to do this now or not? Yeah, I guess we could do it now. What the heck? So the conjugate, of course, takes what's in the numerator, the two radicals, x plus h and root x. But what we do whenever we rationalize something involving radicals is we have to change the sign. So the sign was negative, we're going to make it plus. And notice what I have here in orange is equivalent to 1. So distributing to the numerator, what we get then is the difference of squares. That's how we rationalize. So we get the square root of the quantity x plus h, all squared, from which we're subtracting the square root of x all squared. And then we're dividing that by, there's nothing much I can do in the denominator except list everything. I'll have h times, what color did I use? Orange. The square root of x plus h, to which I'm adding the square root of x. And you'll see why I do this in a moment. Because whenever you square a square root, it gets rid of the square root. So this now becomes x plus h minus x in the numerator all over that big ugly denominator. So I'll just copy and paste that. Copy, paste. But notice that I can reduce x minus x in the numerator. So I'm simply left with, oops, momentito. Where is it? Okay. So I'm simply left with h divided by big ugly denominator. But notice now that the h is reduced. So now I can reduce h over h, which leaves me with simply 1 in the numerator. So this is 1 over the orange guy. The square root of x plus h, to which I'm adding the square root of x. Okay, that was a lot of work, wasn't it? Okay, so let's go on. Let's note. Okay, so to solve a function, so to solve versus evaluate, so now we're on to solve. So to solve a function, we are given its value and must find all values of x that's supposed to be of, that doesn't look like of, so of x for which it holds true, for which it holds true. i.e. id est, i.e. given y, find x. So that's what it means to solve. And what color did I use when I said evaluate? So evaluate, so maybe I should use a brighter color, like gold. So let me rewrite this a bit. So solve in effect means given y, find x. It's the opposite of evaluate, which is given x, find y. Okay, so let's solve some equations. So for example, let's let f of x be equal to 2x squared minus 3x. Solve f of x equal to 5. Okay, so if we have that f of x is equal to 2x squared minus 3x, and we want that this is equal to 5, then we focus on this portion of the equation. So we have 2x squared minus 3x is equal to 5. And we isolate, we want to solve for x, but this is quadratic, so I need to set it to 0. So this becomes 2x squared minus 3x minus 5 is equal to 0. So now I need to factor this. So this is the AC method of factorization. So I say, okay, looking at my coefficients, a times c, 2 times negative 5 is negative 10. So I want two guys that multiply to negative 10 and add to b, which is negative 3. So that looks like that'll be negative 5 and positive 2. So what we need to do then is rewrite our linear term. So 2x squared as positive 2x and negative 5x is the same as negative 3x. So we've just rewritten the linear term with those two. Now I can factor by grouping. So I group the first two, group the second two. What's common to the first two terms is a 2 and an x, leaving me with, maybe I should do a different color, x plus 1 when I factor out. What's common to the second set of 2 is negative 5. When I factor that out, meaning I divide each term by negative 5, I'm left with x plus 1. So now I note that there is an x plus 1 common to both. And when I factor that out, there is a 2x and then a negative 5, which remain. Okay, so setting the first factor to 0, in order for x plus 1 to be 0, x must be negative 1. In order that 2x minus 5 is 0, so 2x minus 5 equals to 0. That means that 2x is 5, which means that x is 5 halves. So my solution, the solution is going to be either negative 1 or 5 halves. So that's the solution that is solving a function. Let's do another one. So example, let's let f of x be equal to the square root of 3x plus 1. Let's solve for f of x being equal to 5. So we're given that f of x is the square root of 3x plus 1, and we want that to be set equal to 5. So we'll just focus on this equation here, namely the square root of 3x plus 1 is equal to 5. So in order to solve for x, I need to square both sides. So I get that 3x plus 1 is equal to the square of 5, which is 25, which means that 3x is 24, which means that, actually, yeah, I hope this monochromatic is not so bad. X is equal to 8, so there we are. There's only one solution there. Okay, so definition. Okay, so if for all y in the range of some function f of x, there exists a unique x such that y is f of x, then this implies f of x is 1 to 1. 1 to 1, denoted by 1 dash 1. Okay, so note one-to-one functions. So 1-to-1 functions pass the horizontal line test, right? The horizontal line test, whereas functions always pass the vertical line test. Hopefully we know that by now. Okay. Do you know what? Maybe I should go back. Now that we're here, let me go back just to prove to you what I just said, which was that functions pass the vertical line test. So let's go ahead and plot these guys. Going out, so let's see. I'm going to show you explicitly. I could just say it, but let me show it explicitly. I think that's better. So x and y. Let me go ahead and plot these points. 1, 2, 3, 4, 5. So we have the points 3, 1, 2, -1, 5, 2, and 4, 1. So notice these pass the vertical line test, right? So no vertical line intersects more than once. So if I have a vertical line, even this one, I've got the same value. So passes a vertical line test, right? And let me prove to you for this one that this one does not pass the vertical line test. So let's see. So x and y. See, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so here we have the points 2, 4, 1, 2, 3, 4. And then we have 2, 3. Then we have 1, 3, and we have 5, 2. So notice there's a problem, and that problem is this line right here. Do you agree that this does not pass the vertical line test because I've intersected 2 points? So does not pass, doesn't pass the vertical line test, VLT. Okay, so hopefully we remember that for functions. So that's just an aside for you guys to remember. Hopefully you do. You know, I don't like the way that looks. It's too cramped. Let me move this up a bit. Okay, so where was I before I went on that tangent? Okay, one-to-one functions, yeah. So one-to-one functions pass a horizontal line test. Regular functions pass a vertical line test as with respect to their graphs. Okay, so now let's look at graphs of standard functions. So the graphs of standard functions, which hopefully you will come to know well. All of these are very important. And we're going to look at whether they're one-to-one. So let's do the first one. Let's say f of x is some constant, so some real number. So this is the constant function. Constant function. So what that looks like, we have our x and y coordinate axes. I'm going to copy and paste this. The constant function looks like a horizontal line. So f of x equals to c. That is what a constant function looks like. And this is absolutely not one-to-one, right? So this is not one-to-one because fails horizontal line test, right? It is a horizontal line, so clearly there's infinitely many points on the horizontal line, not just one. So the horizontal line, if I were to draw a horizontal line right here, would intersect more than one point. Okay, let's look at number 2, which is the line f of x equals to x. So f of x equals to x, which is the identity function. Identity. Okay, so looking at the identity function, what the graph of that looks like is the main diagonal. Oops. There we go. Oops. No, that was off. Okay, there we go. A bit better there. Okay, so this does pass the horizontal line test, right? So if I draw a horizontal line, it only intersects once. So is one-to-one. Okay, let's do another function. Number 3. Let's do f of x is equal to x squared, which is the quadratic function. So the quadratic function is a nice U-shaped graph. Oh, that's a terrible U-shaped graph. So something like so. So f of x equals to x squared. And once again, I can see that this, actually I should have put f of x equals to x up here. I can see that this one will not pass a horizontal line test. So this is not one-to-one. So not one-to-one. Number 4. Let's say we have that f of x is equal to x cubed, which is the cubic function. cubic function. Oops, paste. Okay, so the cubic function is a nice S-shaped graph. It looks something like so. So f of x equals 2x cubed, and this, you'll notice, does pass the horizontal line test. So this is 1-to-1. So is 1-to-1. Next one, number 5. Let's do f of x is equal to the absolute value of x. Oops, absolute value of x, meaning it's always positive. So this is the absolute value function. Absolute value. And hopefully you remember that that looks like a V. So the absolute value function looks like so. So this is f of x being equal to the absolute value of x, which of course does not pass the horizontal line test. Agreed, I intersect more than once, so not 1-to-1. Okay, number 6. Let's say we have that f of x is the square root of x, which is the square root function. So what that looks like is something like so. So f of x being the square root of x, it's only defined where x is positive. So this does pass the horizontal line test because it's always increasing, albeit slowly. So this is 1-to-1. Let's do 7. So let's say we have f of x is, say, the cubed root of x. So that's a cube root function. And much like the cube is a nice S-shaped graph, the cube root is similar, except it's horizontally inclined. Oops. So it looks something like so, as opposed to being vertically inclined, it's horizontally inclined. So this is f of x being equal to the cube root of x, but notice it does pass the horizontal line test. So this is 1-to-1. Let's do number 8. Actually, what color should I use? Let's use this color. So number 8. Let's have that f of x is 1 over x, which is the reciprocal function. So the reciprocal function looks like so and so. It has asymptotes along each axis. So this is f of x being equal to 1 over x. And let me go ahead and put the asymptotes so we see them. So there's an asymptote on the y and the x-axis. So notice that this does indeed still pass. So this is 1-to-1 because it passes the horizontal line test. And last but not least, let's do number 9, 1x. So let's do f of x is 1 over x squared, which is the reciprocal squared. So reciprocal squared. And remember, when you square something, it's always positive. So it'll look similar to the one above, except what's going to happen is that that part that's, oops, negative now becomes positive. So they're both above the x-axis, but the asymptotes are still in the same place. Still the x-axis and still the y-axis. But notice, so this is f of x being equal to 1 over x squared. This one does not pass the horizontal line test, right? So this is not 1-to-1. Actually, that's supposed to be a horizontal line. So this is not 1-to-1. So what I'd like you to do is become familiar with the shapes of these graphs. You know, if necessary, you can plot them by points, but I just want you to get the general idea of what they look like for now. Okay, so we've only got a little bit more to this section. So let's note so we can evaluate which means to find y, right? i.e. given x, find y. And solve. I.e. given y, find x. Functions and relations. Graphically. Okay, so for example, so consider the following graph. So let's say I have something like so, x and y coordinate axes. Let's see, 1, 2, 3, 4, 5, 6. Let's see, what do I want to do? Something like so. X and y. So I want to go down 1, 2, 3 on the y. Let's go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay. So let's say I have something that looks like so. Okay, so I want some graph. Looks something like that. Okay, so this is my function f of x. Oops. So this would be 1, 2, 3, 4. 1, 2, 3, etc. So each tick mark is a single unit. So let's evaluate. F of 0, f of -3, and f of 2, and then let's solve. F of x equal to 2, f of x equals to 0, and f of x equal to -3. I know I'm trying to force it onto this page, but I think we can do it. So, f of 0, meaning x is 0. So x is 0 here, which means the point is -3 for y. So when x is 0, y is -3. Now let's do when x is -3, so 1, 2, 3, y is 0. Agreed? Now let's do when x is 2, y is 2. Okay, so now let's go over here. Let's see, what do we have? Maybe I should do hot pink for one of them, or is that too close to what I've done before? Maybe yellow? I don't know. So we want that y is 2. So y is 2. It looks like there's 2 places where y is 2, at x being -2, right here, and +2. So we've solved for x. Now, when y is 0, well, that's on the x-axis, so 1, 2, 3, 4. There's 4 values of x for which that's true. So that would be when x is 1, 2, 3, -3, -1, +1, and +3. So those are the values on the graph at which y is 0. Okay, now let's do, what color should we use? Guess I could use the hot pink now. So now I want that y is -3. So y is -3 at, oh shoot, well, it looks like there's going to be more values. Do you know what I'm going to do? I'm going to make my life easier. I'm going to stop this function so I don't need to know what those values are. There we go. Cheating. Okay, so I claim that y is -3 when x is 0. Right. Okay, so we've solved this function graphically. Okay, so hopefully that makes sense, and I will see you guys in the next section.